Uh, Hello everyone, I am Himanshu Vasnani from Department of Mechanical Engineering. I am here to discuss with you on the subject non-destructive evaluation and testing. The subject code is ME419, unit number 4 in the series, lecture number 23 in the series, and the topic name for today is magnetic field produced by a coil, hysteresis loop, and magnetic property. Today's learning objective are to provide the students with the basic understanding of hysteresis loop and magnetic properties, and to know about the concept of magnetic field produced by a coil. And the learning outcome of today's lecture will be the students will have an understanding of hysteresis loop and magnetic properties, and the student will understand the concept of magnetic field produced by a coil. So, we have been discussing about the magnetic particle testing in the last lecture, and we studied about the basic principle how it works. Okay, how the MPT magnetic particle testing works. Okay, and we have also discussed about the various types of materials like paramagnetic materials, diamagnetic materials, and ferromagnetic materials. Let's go ahead with the chapter is now the general properties of magnetic lines of force. Now, the magnetic lines of force have a number of important properties which include like they seek the path of least resistance between opposite magnetic poles. That is, in a single bar magnet shown, you can see in the diagram, they attempt to form a closed loop from one pole to another. You can see the how the loops are forming in a bar magnet on the diagram in the right hand side. Okay, then they never cross one another. Okay, they will never cross one another. You can see the how the flow is going. Now they all have the same strength. Then their density decreases with increase increasing distance from the poles. Okay, now the density is decreasing. Okay, with the increase of distance from the poles. Okay, now the density also decreases, as they spread out when they move from an area of higher permeability to an area of lower permeability. I repeat, their density also decreases when they spread out. That is, when they move from an area of higher permeability to an area of lower permeability. Okay, so the density is decreased in two ways. When the distance is increased from the poles, okay, and secondly, when they move from an area of higher permeability to an area of lower permeability, and then they are considered to have directions as if flowing, though no actual movement occurs. Okay, and they flow from south pole to north pole within a material, and north pole to south pole in air. Okay. Now we come to the next topic that is called as the electromagnetic field. Uh, See, it's not only the source of magnetic fields. The flow of electric current through a conductor generates a magnetic field. Okay. Now, when electric current flows in a long straight wire, a circular magnetic field is generated through the wire, and the intensity of this magnetic field is directly proportional to the amount carried by the wire. Okay, I repeat once again, then you'll understand it better. See, when the current is flowing in a straight long wire, okay, a circular magnetic field is generated around the wire. From where the current is flowing, a circular magnetic field is generated along the wire. And the intensity of this magnetic field is directly proportional to the amount of current carried by the wire. So here the intensity of this magnetic field is you can say is important for or you can say it is directly proportional to the amount of current. Okay. Now the strength of the field is strongest next to the wire, and it diminishes with distance. So in most conductors, the magnetic field exists only as long as the current is flowing. See, this we have discussed in ferromagnetic materials and diamagnetic materials and paramagnetic materials that you can say the importance of current in this. So if they say that in most conductors the magnetic field exists only as long as the current is flowing, and they have discussed in the next line only that however in ferromagnetic materials the electric current will cause some or all of the magnetic domains to align and a residual magnetic field will remain. In this way, you can see that in case of ferromagnetic materials, there will, if you remove the current, a residual magnetic field will remain. So also in the direction of the magnetic field is independent on the direction of the electric current in the wire. The direction of the magnetic field around a conductor. This can be determined using a simple rule called the right hand clasp rule. Okay, the right hand clasp rule. It says that if a person grabs a conductor on one's right hand with a thumb pointing in the direction of the current, the thumb is pointing in the direction of the current, and the fingers will circle the conductor in the direction of the magnetic field. Okay, the right hand thumb clasp rule says that if a person grabs a conductor in one's right hand, okay, now you are grasping the conductor in one's in your right hand, thumb will point in the direction of the current, and the fingers will encircle the conductor in the direction of the magnetic field. This is how the right hand clasp rule works. Okay, and you can see the direction of the magnetic field around the conductor. You can determine this with the help of the simple rule. So remember that the current flows from the positive terminal to the negative terminal. That is, electrons flow in the opposite direction. Okay. Now magnetic field produced by a coil. Now this is an also very important topic because you need to understand a coil and then how the magnetic field is produced by a coil. Now, when the current carrying wire is formed into several loops to form a coil, the magnetic field circling each loop combines with the fields from the other loops to produce a concentrated field through the center of the coil. That is, the field flows along the longitudinal axis and the circles back around the outside of the coil. You can see that if in a coil, what do you say that you can say there are several loops of wire in a coil. So the magnetic field circling each loop combines with the fields from the other loops. Okay, it is combining with the fields of the other loops. Okay, uh, to produce a concentrated field throughout the center of the coil. Whether when the coil loops are tightly wound, a uniform magnetic field is developed throughout the length of the coil. This is how the magnetic field works in a coil. They say that when the coil loops are tightly wound, when they are tightly fitted with each other, then a uniform magnetic field is developed throughout the length of the coil. You can see it in the diagram also how you can say the uniformity is there in the magnetic field. Okay. Now the strength of the magnetic field increases not only with increasing strength, but also with each loop that is added to the coil. Okay. Now each loop is, you can say, devoting its presence. Like the strength of magnetic field, it increases not only with the increasing current. Okay, obviously the strength will increase if you increase the current, but with each loop that is added to the coil, every loop has its own dedication in increasing the strength of the magnetic field. A long straight coil of wire is called a solenoid, and it can be used to generate a nearly uniform magnetic field similar to that of a bar magnet. Now they are comparing a straight coil with a bar magnet, and they say that a solenoid, that is a straight coil of wire, okay, it can be used to generate a nearly same uniform magnetic field similar to that of a bar magnet. Okay, now this is what the strength of the coil is. Now the concentrated magnetic field inside a coil is very useful in magnetizing ferromagnetic materials for inspection using the magnetic particle testing method. Now, the importance of coil is there in magnetic particle testing method. Okay. Now, if they say that the concentrated magnetic field inside a coil. Okay. Now, this is very useful in magnetizing ferromagnetic materials for inspection and using the magnetic particle testing method. Okay, we have studied about this magnetic particle testing method previously in the lecture. So the quantifying magnetic properties. So now we are discussing about some properties of magnetic properties that is there. So the various characteristics of magnetism can be measured and expressed quantitatively. Okay, different systems of units can be used for quantifying magnetic, and SI units will be used in this material. Like the advantage of using SI units is that they are traceable back to an agreed set of four base units. Now the units are like meter, kilogram, second, and ampere. So you should understand that these are some SI units that are traceable. Okay, then the names are like meter, kilogram, and seconds and ampere. The unit for magnetic field strength H. H is for magnetic field strength. Remember this technical name. Okay, ampere per meter. Ampere per meter. Capital H stands for magnetic field strength, and it's by ampere per meter. Okay, a magnetic field strength is of 1 ampere per meter is produced at a center of a single circular conductor with a 1 meter diameter carrying a steady current of 1 ampere. Okay, now they are saying, so they are defining this, you can say, unit of that is the magnetic field strength, and they say that a magnetic field strength of 1 ampere per meter is produced at a center of a single circular conductor with a 1 meter diameter carrying a steady current of 1 ampere. Okay, this is how this is simply defined. Okay, how simple they define the magnetic field strength. Okay, so remember capital H stands for magnetic field strength and units are ampere per meter. Okay, now the number of magnetic lines of force cutting through a plane of a given area at right angle is known as magnetic flux density, that is capital B. Another term that you are learning right now, that is magnetic flux density. They say that the number of magnetic lines of force cutting through a plane of a given area at a right angle is known as magnetic flux density, that is capital B. So the flux density or magnetic induction has a Tesla as its unit. Okay, this flux density, magnetic flux density, or you can say that the magnetic induction, this has a unit known as Tesla. Okay, now 1 Tesla is equals to 1 Newton per ampere per meter. Okay, now this is you can say how you are defining Tesla. So a Tesla is given another value, that is 1 Newton for ampere per meter. From these units, it can be seen that the flux density is a measure of the force applied to a particle by the magnetic field. Okay, by the magnetic field, that is capital H. So you can see that this unit, that is a Tesla. Now Tesla is defined. It can be seen that the flux density. See, Tesla represents flux density. So you can say that the flux density, it is a measure of force applied to a particle by the magnetic field. By the magnetic field. So these are simple terms. Okay, magnetic field, then magnetic flux density, capital B. Okay, now you are studying about its unit, that is Tesla. And the total number of lines of a magnetic force in a material is called magnetic flux. Okay, remember the difference between magnetic flux density and magnetic flux. Magnetic flux density is shown by a capital B, okay, and magnetic flux is simply shown by phi. So the total number of lines of magnetic force in a material is called magnetic flux. Okay, the total number of lines of magnetic force in a material is called as magnetic flux phi. So the strength of the flux is determined by a number of magnetic domains that are aligned within a material. Okay. Total flux is simply the flux density applied over an area. So flux carries the unit of a Weber. This is simply a Tesla meter square. I repeat, this is another kind of a definition that is coming in front of you. That is about magnetic flux. They say that the magnetic flux is denoted by phi. So the total number of lines of magnetic force in a material is called as magnetic flux. That is phi. Okay, noted by phi. Now the strength of the flux is determined by the number of magnetic domains that are aligned with a material. Okay, the total flux is simply the flux density applied over an area. Okay, flux density applied over an area, and flux carries the unit of a Weber, which is simply Tesla meter square. Okay, now magnetic flux density capital B is shown by Tesla, and magnetic flux phi is shown by unit Weber, which is Tesla meter square. Now another term, the magnetization capital M, is a measure of the extent to which an object is magnetized. Okay, now you're coming to another, you can say, term that is called magnetization, capital M, is a measure of the extent to which an object is magnetized. So it is a measure of magnetic dipole moment per unit volume of. It is a measure of magnetic dipole moment per unit. Magnetization, it carries the same units as a magnetic field, that is ampere per meter. Okay, it is see, magnetization is a measure of magnetic dipole moment per unit volume of the object. So it carries the same unit as magnetic field, that is ampere per meter. So you have learned about four terms till now: capital H, capital B, phi, and capital M. Okay, now we go further. Now they have shown the some values of these four things that you studied about: magnetization force, at the flux density, and then flux and magnetization, and what units they are shown in this. So here they are saying that in this ampere per meter for the magnetization force, then Tesla for flux density, and for flux Weber, and for magnetization they have shown ampere per meter. This is how they are showing the SI units. Okay, you can see that the magnetization force and the magnetization, they have the four same SI units for them. And now the hysteresis loop and the magnetic properties. Now this topic is really important for magnetic particle testing, because you need to understand the various terms like retentivity, coercivity, okay, then saturation. So these terms will come in your testing time. So you should be aware of such terms. Like when we studied about capital H, capital M, phi, capital B. So these terms were also responsible for in testing. So now we going start with the hysteresis loop and magnetic properties. Now a great deal of information can be learned about the magnetic properties of a material by studying its hysteresis loop. They say that a hysteresis loop shows the relationship between the induced magnetic flux density, that is capital B, and the magnetization force, capital H. You can see in the curve shown on the right hand side, the magnetization force, that is the capital H, is showing the horizontal axis, and the and the magnetic flux density, that is the capital B, plus shown as flux density, is shown by the vertical axis. Okay, then the relationship, that is the Steresis loop is showing, the relationship is between the induced magnetic flux density and the magnetization force. So it is often referred to as the BH curve. BH curve means that is the flux density versus magnetization force curve, or loop, sorry, BH loop. An example of Steresis Loop is shown. You can see on the right hand side how it is shown. So the diagram is quite clear and it is clearly shown now what are the values for the horizontal axis and what is shown on the vertical axis. Now the loop is generated. The loop that you are seeing on the right hand side is generated by measuring the magnetic flux of a ferromagnetic material while the magnetizing force is changed. Okay. Here they say that the curve is between these two. So the loop is between the flux density and the magnetizing force. And now they are saying that the loop that is generated is by measuring the magnetic flux of a ferromagnetic material. Okay, now they have taken a ferromagnetic material. Okay, while the magnetizing force is changed. Okay, now a ferromagnetic material that has never been previously magnetized or has been thoroughly demagnetized will follow the dash line as H is increased. Okay, you can see that it will follow the dash line. Yeah, a ferromagnetic material, they are taking a material that has never been magnetized or it is completely demagnetized. It doesn't have any magnetic forces. And then they say that they will follow the dash line as H is increased. When you increase the magnetizing force, it will follow the dashed line. Okay. Now, as the line demonstrates, the greater the amount of current applied, they say the greater the amount of current applied as H is increasing, the stronger the magnetic field in the component. You can see that the loop is showing that as you are increasing the value of H, then automatically the value of B is also increasing. They say that the greater the amount of current applied, the stronger the magnetic field in the component. Okay, this we have studied in the, you can say, principles of magnetic lines of force. Okay, then or the properties of magnetic lines of force. We have studied in that also. So at a point A, cap small a, they say at a point small a, you can see the small a as the saturation point on the loop. Almost all of the magnetic domains are aligned, and an additional increase in the magnetizing force will produce very little increase in the magnetic flux. They say that at point A, okay, you have reached a point where all the magnetic domains are aligned and an additional increase in the magnetizing force, that is the value of H, will produce very little increase in the magnetic flux, that is the value of B. Now the material has reached the point of magnetic saturation. That is all its magnetic domains are aligned. Okay, the ferromagnetic material is completely magnetized and it has reached the point of magnetic saturation. And if any increase is there, then it will produce a little increase in the magnetic flux only. So it has reached the point of saturation. Okay, the saturation is shown by the small a in the loop. Okay, and if you further increase in the magnetizing force, then it will produce very small, very little increase in the magnetic flux. Okay, now when H is reduced to 0, now comes the variations. Okay, the variations that are shown in the loop. When H is reduced to 0, the curve will move from point A, that is the saturation point, to point B. Okay, you can see the point B that is shown as retentivity. Okay, the point B on the vertical axis. Okay, that is the, you can see the small b, not capital B, small b. Small b is the retentivity point that is given. They say that when the H is reduced to 0, the curve will move from point A to point B. Point B is small b, sorry. At this point, it is can be seen that some magnetic flux remains in the material even though the magnetizing force is 0. They say, see, it is a property of ferromagnetic materials. Okay, if you remove the magnetizing force, even though there will be some magnetic flux. So we have taken ferromagnetic material here. So here it is saying that it can be seen that that some magnetic flux remains in the material even though the magnetizing force is 0. This is referred to as the point of retentivity on the graph. in the loop, you can say, and it indicates the level of residual magnetism in the material. That is, some of the magnetic domains remain aligned, but some have lost their alignment. Okay, so it is the property of ferromagnetic materials that they have a level of residual magnetism. Okay, so when you can see in the this loop also that the point B, it is referred to as, sorry, small b. Okay, small b is referred to as the point of retentivity on the graph, and it indicates the level of residual magnetism. Now, further moving ahead, as the magnetizing force is reversed, the curve moves to a point small c, where the flux has been reduced to zero. This is called as a point of coercivity on the curve. That is, the reverse magnetizing force has flipped enough of the domains so that the net flux within the material is zero. Okay, now it is going on the reverse direction, that when the magnetizing force is reversed, the curve moves from point B to point small c, where the flux has been reduced to zero, and this is called as a point of coercivity. You can see in the loop the small c point is it's shown as coercivity, which is shown as point of coercivity on the curve. Okay, and this means that the reverse magnetizing force has flipped enough of the domain so that the net flux within the material is zero. Now, the force required to remove the residual magnetism from the material is called as coercive force or coercivity of the material. Now, this is giving you another term that is called as coercivity of the material, and it says that this is the force required to remove the residual magnetism from the material. Required to remove the residual magnetism from the material is called as coercive force or coercivity of the material. Now we studied about points small a, small b, and small c. Okay, now we are going further. As the magnetizing force is increased in the negative direction, now you are increasing the magnetizing force in the opposite direction, in the negative direction. The material will again become magnetically saturated, but in the opposite direction, that is at point small d. You can see the point small d in the diagram on the right hand side. It is written as saturation in opposite direction. Saturation in opposite direction. Okay, reducing H, that is the magnetizing force, to zero brings the curve to point E, small e. Okay, it will have the level of residual magnetism equal to that achieved in the other direction. Okay, now what they are doing, they are again, you can say, saying that reducing the value of magnetizing force. Okay, that is H to zero. Okay, now this is will again bring a change. That is, the change will be that it will bring the curve to point D, sorry, small e. It will bring the curve to point small e from D to point E, and it will have a level of residual magnetism equal to that achieved in the other direction. Okay, now increasing H, that is the magnetizing force, back in the positive direction will return B to zero. This will return again B to zero. Notice that the curve did not return to the origin of the graph. Now here you can see that since the loop is going small a, small b, small c, small d, small e, small f, okay, you have increased the magnetizing force, you have reduced it to zero, then in the negative direction, and then again reduce it to zero. Now you can see that the curve did not return to the origin of the graph because some force is required to remove the residual magnetism. Okay, some force is required to remove the residual magnetism. Okay, the curve will take a different path from the point F. Why? Because you still require some force to remove the residual magnetism. And they say that the curve is moving from a point F back to the saturation point, that is point A, from where from where from back to saturation point where it will to complete the loop. Okay, it is going to point A to complete the loop. So here the loop, you can see that small a, small b, small c, small d, small e, small f, and then back to the small a. This is the loop that is following. This is called as hysteresis loop. Okay, so each point has its own importance. Like saturation has its own importance. Okay, it has reached the maximum alignment. Then retentivity has its own importance. Then coercivity has its own importance. Then if you go ahead to the point D, then it is a saturation point, but in opposite direction. Okay, then E has its own importance. F has its own importance. So you can see the loop, how it is giving you the different values. Okay, and from the Steresis loop, a number of primary magnetic properties of the material can be determined, like retentivity. Now, retentivity is a measure of residual flux density corresponding to the saturation induction of a magnetic material. Okay, in other words, you can say that is the material ability to retain a certain amount of residual magnetic field when the magnetizing force is removed after achieving saturation. I repeat, retentivity is the material's ability to retain a certain amount of residual magnetic field when the magnetizing force is removed after achieving the saturation. That is the value of capital B at point small b on the hysteresis curve. You can see the retentivity word written on small b. Okay. Now here we are using a ferromagnetic material for studying this loop. Okay. Now residual magnetism or residual flux. Now the magnetic flux density that remains in a material, the magnetic flux density that remains in a material when the magnetizing force is zero. Okay, note that the residual magnetism and retentivity are same when the material has been magnetized to the saturation point. However, the level of residual magnetism may be lower than the retentivity value when the magnetizing force did not reach the saturation level. Okay, here they're saying that the the residual magnetism and retentivity are the same when the material has been magnetized to the saturation point. Okay, now the level of residual magnetism may be lower than the retentivity. Okay, when the magnetic force did not reach the saturation level. Now the coercive force. They say that the amount of reverse magnetic field which must be applied to a magnetic material to make the magnetic flux return to zero. Okay, the coercivity point, capital sorry small c, is there. You can see in that the amount of reverse magnetic field which must be applied to a magnetic material to make the magnetic flux return to zero. That is the value of the value of capital H at point small c on the Stasis curve. Okay, this is how they are defining the coercive force, or you can see coercivity. Okay, so this is the small c point on, you can say, in the loop. Now permeability. Okay, permeability. They say this is noted by mu, a property of a material that describes the ease with which a magnetic flux is established in the material. Okay, the ease with which the magnetic flux is established in the material. It is called as permeability. Okay, now reluctance, another term. It is the opposition that a ferromagnetic material shows to the establishment of the magnetic field. Okay, this is the opposition that a ferromagnetic material shows to the establishment of a magnetic field. Now you can say the ferromagnetic material, which is you can say which is so much used in magnetic particle testing. It also shows opposition. Okay, and it is you can say known by reluctance. So reluctance is the analogous to the resistance in an electrical circuit. Okay, now permeability. Okay, permeability. One of the important topic that we have just defined before, that it is a property of a material that describes the ease with which a magnetic flux is established. The ease with which the magnetic flux is established in the material. Now you are going more in permeability. Okay, so they say that it is the ratio of the flux density. It is the flux density, that is capital B, created within a material to the magnetizing field, creating within a material to the magnetizing field, that is capital H, and is represented by mu is equals to capital B upon capital H. Now you can see in the diagram on the right hand side, they are showing only the 1/4 part of the loop. Okay, that is from that is the saturation point that you are seeing. So there you will see that the permeability is defined as the you can say material property, that is the ease with which a magnetic flux is established in the component, and it is shown by the ratio of the flux density, that is capital B, created within a material to the magnetizing field capital H. So it is shown by mu capital is equals to capital B upon capital H, where capital B is flux density and capital H is magnetizing field. Okay, you can also see in the right hand side of the diagram also. So this equation, it describes the slope of the curve at any point on the Steresis loop. The permeability value given in literature for materials is usually the maximum permeability or the maximum relative permeability. Okay. So the maximum permeability is the point where the slope of the this BH curve, permeability curve, for the unmagnetized material is the greatest. Okay. They are saying that the maximum permeability is the point where the slope of the BH curve for the unmagnetized material is the greatest. Here the permeability is greatest. And this point is often taken as a point where a straight line from origin is tangent to the BH curve. Okay. Now here you can see that you can say slope is given, and they say that the slope of the line that is tangent to the BH curve at this point is used to determine material's maximum permeability. Okay. Now the shape of the Steresis loop tells a great deal about a material being magnetized. The Steresis curve of two different materials, like is shown there. Now, relative to other materials, a material with a wider hysteresis loop, you can see that there are two curves shown, red and blue. Okay. Now, if you have in the wider hysteresis loop, okay, you can see that it is showing that it has lower permeability and it has higher retentivity, it has higher coercivity, it has higher reluctance, and it has higher residual magnetism. This all terms are relative to the material with a wider hysteresis loop. Okay, and then the related to other materials, a material with narrower hysteresis loop, it will have higher permeability, it will have lower attentivity, it has lower coercivity, it has lower reluctance, it has lower residual magnetism. So these are, you can say, the terms which are, you can say, yeah, or you can say the depth, you can say the understanding which you have obtained with the study of this hysteresis loop. Well, if you have a wider hysteresis loop, then what all values will you have, and if you have a narrower hysteresis loop, you understand what all values will you have. So this is just an idea with the help of this diagram you can understand. So let's Let's start with the MCQ now because it is time. Now, in the MCQ, let's start with the MCQ. The first question says that a circular magnetic field has a magnetic lines of force that run circumferentially around the perimeter of a part. A circular magnetic field is induced in an article by either passing current through the component or by passing current through a conductor surrounded by a component. So what do you say? It is about the circular magnetic field. So it is true or false? It is true. Okay, true. Now, a component with high carbon content will have low permeability and will retain more magnetic flux than a material with low carbon content. It is true or false? What do you say? It is true. A component with higher carbon content will have low permeability and will retain more magnetic flux than a material with low carbon content. Now, a longitudinal magnetic field has magnetic lines of force that run parallel to the long axis of the part. Parallel to the long axis of the part. Longitudinal magnetization of a component can be accomplished using the longitudinal field. Okay, it can be accomplished using a longitudinal field set up by a coil or solenoid. It can also be accomplished using a permanent magnets or electromagnets. So it is true in this case. It is true that it can be accomplished with a permanent magnets or electromagnets. Uh, in magnetic particle inspection, it is the property of the material that describes the ease with which a magnetic flux is established in the material. We have just discussed this property of the material a few moments before. What do you say? It is permeability. It is permeability, noted by mu. In magnetic field inspection, it is the opposition of that a ferromagnetic material shows to the establishment of a magnetic field. It is the opposition of a ferromagnetic material which shows to the establishment of a magnetic field. What do we call this? We call this as reluctance. What do you call this? We call this as reluctance. That is, it is shown by the answer C. Okay, it is the opposition that a ferromagnetic material shows to the establishment of a magnetic field. Okay, okay, the magnetic field is, you can say, resisted by this. So it is called a reluctance. Now, in magnetic particle inspection, it is the material's ability to retain a certain amount of residual magnetic field when the magnetizing force is removed after achieving saturation. It is the, in MPI, magnetic particle inspection, it is the material's ability to retain a certain amount of residual magnetic field when the magnetizing force is removed after achieving saturation. So what do we call this? We call this as retentivity. We call this as retentivity. That is a material's ability to retain a certain amount of residual magnetic field when the magnetizing force is removed after achieving saturation. Okay. Normally we obtain this in ferromagnetic materials. Okay. Normally we obtain this in ferromagnetic materials. Now, in magnetic particle inspection, any place that a magnetic line of force exists or enters the magnet, the pole. It is true. You know the South Pole and the North Pole. Okay, so it is any place that in any place that a magnetic line of force exists or enters the magnet called as the pole. Okay, next. In magnetic particle inspection, the magnetization, capital M, is a measure of the extent to which an object is magnetized. Okay, as the term says, magnetization. So it is a measure of the extent to which an object is magnetized. So it is a measure of the magnetic dipole moment per unit volume of the object. So this is capital M magnetization, and they say that it is the measure of the extent to which an object is magnetized. So what do you say? True or false? It is true. It is true that the capital M is shown to you for getting the object magnetized. Okay. So it is the measure of the extent to which the object is magnetized. Okay, so remember capital M in this. Now the next is ninth question. A hysteresis loop shows no relation, shows the relationship between the induced magnetic flux density, that is B, and the magnetizing force F. A Stasis loop, it shows the relationship between the induced magnetic flux density, that is capital B, and the magnetizing force, capital H. So here you will see that in this the hysteresis loop relationship is given that it shows the relationship between magnetic flux density, that is capital B, and magnetizing force. It is true. It is true also here in this case. Then in magnetic particle inspection, Uh, okay, let me just give you one more idea of this. We have studied about this terms like in this loop, like capital, sorry, small a, small b, small c, small d, small e, small f. So if you remember that the uh, here how the changes were there when you are increasing the magnetizing force and then decreasing it and again increasing and again decreasing. So because you have seen the variation in the loop for this. So you can remember by this that it is the relationship between the induced magnetic flux density and the magnetizing force. So here you will easily remember what is the answer. So it is true. Okay, it is true. Now, when the magnetic particle inspection, it is the amount of reverse magnetic field which must be applied to a magnetic material to make the magnetic flux return to zero. So what do you call this? We call this as coercive force. Coercive force. This is the amount of reverse magnetic field you are applying to a magnetic material. Okay, to make the magnetic flux return to zero. Now you are making the magnetic flux return to zero. You are applying reverse magnetic field force. So what do you call it? We call it as coercive force. It is called as a coercive force. So answer B is the answer. Coercive force. So now we have completed with our uh, topic for today, and here are the references which you can refer. These references will help you to increase the knowledge in the current topic, and hopefully, you if you read them, then also you will get some knowledge. Okay, and the knowledge is good when you read books. Thank you all.